Good morning. Today I wanted to spend some time at the beginning of class going over the challenge problem from yesterday. This is actually the second time that you've seen a problem similar to this, and you've actually seen kind of a variation of problems like this when you watched the couple videos on redox titration challenge problems in class. So this shouldn't be necessarily something that's new to you, but it might just be a little bit challenging for you to work through. There's a lot going on in a problem such as this, and so I wanted to take some time and take a look at it with you. Now, with that in mind, y'all, I need you to understand one thing really quickly, and that is that there will not be a problem like this on your exam. There will not be a problem like this on your exam that's on Thursday. However, moving forward, you will get to a point where you're going to see problems like this on your exams. These are problems similar to the sort of short answer questions that you would see in the short and long response on the AP exam if you decided to take it. So this is just going to give you a chance to practice getting familiar with AP level questions, to practice getting comfortable with, working through and working with the information you have and problem solving to figure out how you go about answering a question. So let's just go ahead and take a look at it. So it says sodium nitrite, which is NaNO2, is used as a preservative in meat products such as hot dogs and lunch meats. In acidic solution, nitrite ions are converted to nitrous acid, which is HNO2. Which is HNO2, which reacts with the permanganate according to the following unbalanced equation. Now, a few things to notice about this unbalanced equation before we do anything with it. Notice that we've got this hydrogen here, and all that really is telling us is that it is in an acidic solution, and that's why we see hydrogen ions present, right? It even tells us that, right, in an acidic solution. The other thing we notice is that we've got this nitrous acid. Now notice it's not dissociated. Notice it's not aqueous. And that's actually because nitrous acid is a weak acid, or you could say a weak electrolyte, which means what? Well, it means that it doesn't ionize very well. All right, so in terms of and weak electrolyte, that was one of your words that we looked at the very beginning of this unit in terms of solubility, but a weak electrolyte just simply means does not ionize well. So it doesn't become ions like a strong acid would, right? Like if we were looking at a strong acid, then we could actually break it apart, and we could see that it might be something like hydrogen and chloride, or hydrogen and sulfate, and so on. So again, HNO2. And then you see the MnO4. The MnO4 is really just permanganate, right? That's permanganate. And then notice it reacts to produce nitrate ions. Notice the nitrate ions are by themselves. And really that's just because why? Because they're aqueous, right? They are aqueous in pretty much everything they attach to. Notice the manganese ions, and then notice the water. And all that water really is there for is because in the end this is going to be a redox reaction, which means there's going to be some water that might be produced from the acid. Alright, so it gives us some more information. It says that we have 1 gram sample of a water-soluble solid containing NaNO2, and that it was dissolved in dilute H2SO4. Now this is important, y'all, because all this is really telling us, remember we said it was put in an acidic solution, right? So all this is really telling us is it's telling us what the acid is. It's telling us how we're getting that acidic solution, right? So we dissolved it in sulfuric acid, and that's how we're getting that acidic solution. Sulfuric acid being a strong acid, able to dissociate very well. Notice it says and titrated with 0.01 molar potassium permanganate solution, and the titration required 11.6 grams of it. Now, keyword or words, you see them twice. You see titrated or the word titration. We actually talked about this word back in one of your previous video lessons when we were looking at one of your other challenge problems, but let's just review, or if you don't know what this word means, let me just mention to you that in terms of what we mean when we say titrated or titration, is it simply means that stoichiometrically speaking, we have equal amounts stoichiometrically of our reactants. So what does that mean really in general terms? It just simply means that we have enough of one reactant to completely use up the other. You think about when we've talked about all the reactions we've ever done in class, in Chem 1 or even any that you've done now, you generally always see words that say things like excess or limiting, right? Which implies that one runs out, right, limiting, while the other one has extra of it. But in a titration, the idea is that they both are used up. So you use just the right amount of one to react all of the other. That's the idea, all right? So in other words, in a titration, there's nothing in excess, there's nothing limiting. It simply is the right amount of both together to produce the reaction, stoichiometrically speaking. All right, so that's the idea. So in terms of that means that everything we're looking at ultimately using stoichiometry to solve. But let's just think about where we should start. So let's just picture what's going on. And in order to do that, I'm going to click off of this slide for just a minute so that you can picture what's going on in this problem. Now, the problem had said, remember, that we had a sample, and in this sample that we actually had 1 gram of the sample, but in the sample we had a substance that was NaNO2. Now, right? Now, when we think about NaNO2, it is aqueous. It has to be because of that sodium. Sorry. So really, in this solution, this little beaker, this solid substance with that NaNO2, if we add water to it, right? If we add water, well, really we have just Na plus and NO2 negative, right? So we've got aqueous ions of sodium and nitrite. Now, why is that important? Well, remember that we actually put it into solution by adding sulfuric acid, right? So we didn't just add water to it to dissolve it. We actually added sulfuric acid. Now, we picture this. Really what we have then, because both of these substances are aqueous, is we have sodium and nitrite reacting with hydrogen and sulfate. And when these react, think about what we're producing, right? We're producing sodium. So if we were to react this is a double replacement reaction, right? So really we've got sodium sulfate and nitrous acid. Technically both being aqueous, but this is what? This is a weak acid, so we don't see dissociation. Alright, so with that in mind, what happens to these products? Now let's think about it. So we've got sodium, we've got sulfate, we've got nitrous acid, right? And it simply does not dissociate. Why? Because it is a weak acid. So in terms of looking at this reaction, really, you think about it, you balance the equation, so put a 2 here, put a 2 here, put a 2 here, and then we can get rid of our spectators, right? And really what we're left with is 2 NO2 negative plus 2H plus yields 2HNO2. So really we could reduce that, right? Which means it becomes NO2 negative plus H plus yields HNO2. So we see, in other words, where this HNO2 is coming from. How is it that we're starting with this sodium nitrite, and in the end, really, as the reaction told us, it told us that we were taking that nitrite and that we were really getting nitrous acid, right? So the question was how, and that's how. Now think about then what it tells us. It tells us that this nitrous acid was then titrated with potassium permanganate, right? So potassium permanganate, which is really just KMnO4. Now, again, nitrous acid is a weak acid, so it doesn't dissociate well, but the potassium permanganate does, right? So we picture what the product should look like here. If this HNO2 does not, dissociate, well, then it's still HNO2, but the potassium permanganate does, right? So it becomes K plus and really just MnO4 minus. So by adding this KMnO4 to solution, all we're really getting is that nitrous acid and the potassium and the permanganate. Now, let's talk about what this tells us actually happens, because really we're not producing these things as products. So really, if we want to picture what's going on, we need to take a step back and we need to realize that this potassium permanganate is in solution, right? So this nitrous acid and potassium and permanganate, it tells us really is producing what? Well, it tells us it's producing, sorry, not that, but it's actually producing nitrate and manganese and some water, right? So we're going to have some hydrogen ions in there. We're going to have nitrous acid, we're going to have potassium, we're going to have permanganate, and we're going to end up producing all these things. Now let's think about where these hydrogen ions are going to come from, because technically this is our equation before balancing, right? Before balancing with redox, this is our equation. And truly, I should have potassium over here as well, which is why potassium actually is gone. So really, our equation is just nitrous acid and permanganate makes nitrate and manganese. So the question is, how does that happen? And the only way we'd be able to figure that out is by, well, let's just look at what the first question asks us, right? The redox reaction using the half reaction method. So let's remember what our half reaction just was, because, well, our whole reaction, we had come up with the idea based on all that information that our reaction was nitrous acid and permanganate yielding NO3 negative, and manganese, and the question was, what should the half reactions look like? So let's go ahead and figure them out. Now I'm going to go ahead and write out the half reactions and then look at their oxidation states, but hopefully you can see that the nitrite is going to become nitrate, right? So that's going to be one of our half reactions, is that nitrite becoming nitrate. Our other half reaction is going to be that permanganate becoming manganese. All right? All right, let's look at the oxidation states. All right, so let's start here. We know oxygen -2, so a total of -4. Hydrogen's always +1, so nitrogen has got to be +3. Over here, oxygen is -2, so a total of -6. Net -1 charge, so nitrogen has got to be +5. All right, so what's going on there? If we're starting with +3 and we're ending with a charge that's +5, what's causing this to become +5? Well, it's becoming more positive, right? It's becoming more positive because why? Because it's losing 2 electrons. It's being oxidized. Remember, oxidized is to lose electrons. Remember, anytime that happens, the electrons will be products. Okay, so let's talk about the permanganate becoming manganese. All right, so we got oxygen -2 for a total of -8. Notice a net -1 charge, so that means manganese has got to be +7. It starts as +7, becomes +2. What's happening? Notice that it's becoming reduced, right? It's becoming more negative because why? Because you are gaining electrons. It's being reduced. Why? It's gaining electrons. Again, something to remember. If it's reduced, the electrons will be reactants. Alright, so there we go. We've got our electrons in there. What's the next step? Now the next step is to balance the charges. Again, remember it's based on acidic or basic solution. It tells us this is an acidic solution, which means we're going to balance the charges with hydrogen. So notice right here, we have no net charge over on this side. We've got a net charge of -3 over here, right? We've got 2 negative and a 1 negative, so a total of -3, which means we need 3 hydrogen ions. That's going to give us a net of 0, which means the charge on the product side equals the charge on the reactants. All right, let's do the same thing for manganese and manganate. All right, so we've got 5 negative, 1 negative. That's a total of 6 negative on the reactants. We've got 2 positive on the products. So we're going to end up with 8 positives on the reactant side. 8 hydrogen ions, which are positive. 6 negative charges would give us a net of +2 on both sides of our equation. Alright, so our charges are balanced. Next step, remember, is to balance the oxygen and hydrogens by adding water. So let's start up here. Notice that one of our hydrogens is always already accounted for, which means really we've got only 2 hydrogens we need to worry about. So we're going to add 1 water. By adding 1 water, we've now got 3 hydrogens on the reactants, 3 hydrogens on the products. Notice we've got 3 oxygens in the reactants, 3 oxygens on the products, and now our equation is done. It's balanced. Everything is balanced, charges and the atoms. Alright, so let's go look at the bottom one. Alright, same idea. Notice we've got 8 hydrogens on the reactant side, none of them on the product. So remember that generally speaking, based on the hydrogen, we'll add half as many waters. So 8 hydrogens means 4 waters on the product side. When we do that, we now have 8 hydrogens on the reactants and products, 4 oxygens on the reactants and products. Manganese was already balanced, charges are already balanced, and we're done. Alright, next, notice that, again, our electrons, technically, while they are equal for each half reaction, they're not equal between reactions, and they need to be, right? We can't produce 2 electrons, but yet use 5. So we're going to have to make them equal, least common multiple. So for here, it's going to be 5. For here, it's going to be times 2. So let's do that. We've got 5 waters plus 5 HNO2s yields 5 NO3 negatives plus 10 electrons plus 15 hydrogens. Alright, same idea at the bottom one. 2, we've got 16 hydrogens plus 10 electrons plus 2 permanganate ions yields 2 manganese plus 8 waters. Alright, so we've got our two half reactions completely balanced. Now our electrons are the same between the two half reactions. Now we want to cross out anything that's the same on both sides. We call those spectators, and be left over with our redox reaction. So obviously electrons I got to cancel. Next, notice we got 16 hydrogen, 15 hydrogen, so we've got a net of 1 hydrogen. Notice 5 waters and 8 waters, so a net of 3 waters, and now we can write our balanced equation. We've got 1 hydrogen plus 5 HNO2s plus 2 MnO4 negative yields 5 NO3 negative plus 2 Mn plus 2 plus 3 H2O. It's a whole lot of writing, but that is our balanced redox reaction. And while we're not done, that at least puts us through answering that first question to balance the redox reaction using the half reaction method. Okay, let's go ahead and let's continue on, and let's look at the next question that's asked on this challenge problem. So I'm going to move from this slide. If you should need to look or write anything down from this slide, please feel free to pause the video and go ahead and jot down what you need to, and then we can or you can continue on. All right, so the next question said how many moles of nitrous acid were titrated by the potassium permanganate solution. Now, in order to answer this question, let's go back and let's consider a few things. So I'm going to go ahead and I'm going to rewrite my balanced redox reaction again, just so we have it. So it was H plus 5 HNO2 plus 2 MnO4 negative yields 5 NO3 negatives plus 2 Mn plus 2 plus 3 waters. Now let's look at the information we've been given, and let's remember that what we were told in this problem is that we were titrating a 0.0100 molar solution of KMNO4, and that we were using 11.60 milliliters of it. Now, in order to picture what we're doing, let's talk again about the potassium permanganate. And let's remember that when potassium permanganate is in solution, that really it's just potassium and permanganate. Which means, if you had 0.0100 molar of potassium permanganate in solution, really you've got 0.0100 molar of potassium and 0.0100 molar of permanganate, right? Because stoichiometrically speaking, they're all in a 1-to-1 ratio. So whatever we have for these values, we really could just look at them in terms of permanganate since their ratio is the same. So, and we know that the molarity in this problem of the permanganate is 0.0100 molar. We do not know moles but we do know liters. We technically know milliliters, but we can convert that to liters, and really convert it to liters, it just becomes 0.0116 liters of sulfur moles, right? We could simply convert sulfur moles, and we get that there are how many moles of permanganate ions? Well, we get that there's 0.000116 moles of permanganate. All right, that's great. The question is, how many moles of nitrous acid were titrated by that? Now remember, we said that all this really means is that we're using stoichiometry. It really just means that for every how many moles of permanganate, we need to have, stoichiometrically speaking, the same equivalent of the nitrous acid. So all we really got to do is convert using stoichiometry. So if we've got 0.000116 moles of our permanganate, and we're told, based on our balanced redox equation, that for every 5 moles of nitrous acid, we would use 2 moles of permanganate. Well, we can really just solve it, right? For every 5 moles, we would use 2 moles. And so it's just a matter of setting up a dimensional analysis problem, and we get that there's 0.00029 moles of our nitrous acid. Okay, so that answers that question. Now the next question says, how many grams of sodium nitrite were originally present in the sample? So let's think about what we're being told. We know that there's 0.0029 moles of HNO2 being produced. Now if all of the nitrous or nitrite is reacting, if we've got all that nitrite there, then really all that's saying is what? If it's saying that if we go back to that original equation, so remember in that original equation that we had, we said actually becomes sodium and nitrite, then really all this is telling us, based on our equation, again, going back to the equation that we had from the very beginning, when we were trying to picture what was going on here, we have 2Na plus 2NO negative plus, remember, our sulfuric acid. Remember, and we said that that produces what? That it produced our nitrous acid plus our Na plus our SO4, right? And we even balanced it by putting some 2's. And this was our equation all the way back from the very beginning. This showed us how we made this nitrous acid. So if we work our way backwards, if this is how much of this nitrous acid that we had, this many moles, then again, stoichiometrically speaking, we should have that many moles of nitrite to begin with. So let's just take a look. If that's how many moles of nitrous acid we had, and it tells us for every 2 moles of nitrite, we're producing 2 moles of, for every 2 moles of nitrous acid, we're producing 2 moles. There we go. For every 2 moles of nitrite, we're producing 2 moles of nitrous acid. Well, really, we just have the same amount of moles of nitrite to begin with. So that's what it should look like, right? So we've got the same amount of moles of nitrite. Why? Because that's all nitrite really is. It's a part of nitrous acid. HNO2 negative is really just hydrogen and nitrite. So we've got moles of our nitrite to begin with. If really nitrite is just equal parts sodium, and then the nitrite to give sodium nitrite, well, we could just proportionally change it back, right? 1 mole of NO2 negative is equivalent to 1 mole of NaNO2. So we really just have 0.00029 moles of NaNO2. But that's not what the question asks. The question asks for grams. So let's go ahead and finish this problem. Now it just becomes dimensional analysis using molar mass. We have NaNO2 in moles. So we need grams of NaNO2 on top over 1 mole. You look, you find the molar mass. You see it's 69 grams of NaNO2. So you multiply, and you end up with 0.020 grams of NaNO2 to begin with. So in that sample, only 0.02 grams of it was sodium nitrite. All right, last question. What was the percentage of sodium nitrite in the original sample? So percentage should just simply be the mass over the total mass times 100. So really our mass of the sodium nitrite was 0.020 grams. Our sample was 1 gram of sample times 100, and we end up with, it's only about 2% sodium nitrite. So a very small amount of that sample is actually the sodium nitrite that's used for the production of the preservative. Alright, y'all, that's it. Now, look, there's a lot going on there. You might want to pause the video and jot some of this down, maybe even play some of the video again. If you should have any questions about any of it, please don't hesitate to ask. Let me remind you really quickly that this kind of question will not be on your exam. However, as you move forward, you will start to see questions like this on some of your future exams, as well as there will be questions similar to these as you get to the long response and short response on the AP exam in chemistry. Really quickly, I wanted you to jot one last thing down. If you need to pause the video to write some of this down, do it, and then start it again. But I wanted you to just jot down this for me real quick, and that is your format for your exam. Remember these things. You're going to have to know information about solubility. That includes strong, weak electrolytes. That includes aqueous versus not. That also includes net ionic equations and precipitates. Also, you're going to have to be able to solve calculations related to molarity. That includes when you start with a solid or when you're working with a dilution. And then lastly, you're going to have to do some redox. That includes oxidation states. So perhaps you're just determining the oxidation states. You could be determining what's oxidized or reduced. And lastly, you could or you will have one redox reaction. And I'll go ahead and tell you that it will be in an acidic solution. And that's it, y'all. If you should have any questions, please do not hesitate to contact me. Otherwise, please make sure you study for this exam, and I hope you have a great day. Goodbye.